Welcome to the session metric space, boundedness, compactness and connectedness. Definition 1. A set is bounded when the distances between any two points in the set have an upper bound. The least such upper bound is called the diameter of the set. Diameter of the set B equal to supremum of distance between x comma y such that x and y belongs to the set B. Example: the set right opened interval AB is bounded in R because distance between x comma y less than or equal to b minus a for any two elements in the right open interval AB. In fact, the diameter of the right opened interval AB is equal to b minus a. The set R is unbounded because distance between 0 comma y equal to mod y can be made as large as needed. Note that boundedness is a property of how large a set is. However, it is not a good metric property. If B is a bounded and f is a continuous function, then fb need not be bounded. Thus, a set may be bounded in one metric space X, but not remain so when X is deformed continuously to another. Proposition 1. A set B is bounded when it can be covered by a ball, that is, B is subset of BRA where R greater than 0 and A belongs to X. For example, the set right opened interval 0 1 union open interval 2 3 is bounded because it can be covered by the ball B for 0. Definition 2. A set B is totally bounded when it can be covered by a finite number of epsilon balls, however small epsilon. That is, for every epsilon greater than 0, there exists A1, A2, etc. An, B subset of union I varies from 1 to n B epsilon Ai. Example: the set closed interval 0 1 is totally bounded because it can be covered by the balls for n equal to 0, 1, 2, 3, etc. n, where n is greater than 1 by epsilon. Proposition 2. A totally bounded set is bounded. Proof. Let B be a totally bounded set. Therefore, we can cover it by finite number of epsilon balls, in particular by 1 balls. That is, B is fully contained in union I varies from 1 to n B1 Ai. Since there are only a finite number of these balls, we can find the maximum distance between their centers. That is, D is equal to maximum of distance between Ai comma Aj. Now, given any two points x comma y in B, they must be covered by two of these balls B1 Ai and B1 Aj, say. Therefore, using the triangle inequality twice, d of x comma y is less than or equal to d of x comma Ai plus d of Ai comma Aj plus d of Aj comma y, which is less than or equal to 1 plus d plus 1. That is, d plus 2 is an upper bound for the distance between 2 points in B. Compactness. We define compact set to be the closed and bounded set in R2. However, the definition of compact is not exactly the same in metric space. Definition 3. The set S is compact if any infinite sequence in S has convergent subsequence in S. From the definition, it is very easy to see that a compact set is closed in any metric space. However, in general, closed and bounded does not imply compact. We can see that we need the concept of convergence, hence metric, in the definition 3. Definition 4. Let C be the collection of some open sets. If S is subset of union of U where U belongs to C, then we say that C is an open cover of S. C is called a finite cover of S if C is an open cover of S with finitely many elements. D is called a subcover of S with respect to C if D is fully contained in C and S is fully contained in union of U where U belongs to D. For example, C equal to set of all intervals 1 by n comma 1 such that n belongs to n is an open cover of open interval 0, 1 but not of closed interval 0, 1. If we add the intervals open interval minus 0.1 comma 0.1 and open interval 0.9 comma 1.1 to C, then C is an open cover of closed interval 0, 1. Theorem 1. S is compact if and only if every open cover of S has a finite subcover. The second part of the theorem means that for an open cover C of S, there exists D subset of C with finitely many elements, where D is a cover of S. Here C may have uncountably many elements. Proof. Suppose S is compact and there is an open cover C which cannot have a finite subcover. Exclude those elements in C which is a subset of the union of other elements. Therefore, for any U belongs to C, we can choose X belongs to C such that if U not equal to V belongs to C, then X does not belongs to V. Now, for each Ui, pick Xi in such a manner. As no finite cover with respect to C exists, set Xi forms an infinite sequence. Hence, there is a subsequence converging to X in S. Now, X belongs to U for some U belongs to C. This U contains infinitely many Xi contradicting the choice of Xi. Conversely, suppose there is an infinite sequence Xi which does not have convergent subsequence. Then for each X belongs to S and Xi not equal to X for any I, there is Rx greater than 0 such that B of X comma Rx contains no Xi, or if X equal to Xi, there is Rx greater than 0 such that B of X comma Rx contain one Xi only. Now, C equal to set of all B of X comma Rx such that X belongs to S is an open cover of S which does not have finite subcover, a contradiction. This completes the proof. Example. The right opened interval 0, 1 is not compact because the cover of balls for n equal to 2, 3 etc. has no finite subcover. Similarly, the sets R and N are not compact, but the sets open interval AB are compact. Proposition 3. Any closed subset S of a compact set K is compact. First proof. For an infinite sequence Xn in S, it has a subsequence converging to X in K. Then X is a limit point of S, hence in S. This proves the compactness of S. Second proof. Suppose S is fully contained in union U alpha, where U alpha is open. Let U equal to X difference S, which is open. Then U alpha and U together form an open cover of K. Since K is compact, from this open cover there exists a finite subcover, which means K is fully contained in union U alpha I union U for I equal to 1 to n. Hence, S is fully contained in union U alpha I, where I varies from 1 to n. We have found a finite subcover of S. Remark. The second proof does not involve metric. It will be the proof of the theorem in topological spaces. Corollary. Any intersection including uncountable of compact sets is compact. Proposition 4. Finite union of compact sets is compact. Proof. Let K equal to union Ki, where I varies from 1 to n, where Ki is compact and C be an open cover of K. Now, for each Ki, we pick finite elements of C to form a subcover Ci. Now, union Ci, I varies from 1 to n, is a finite subcover of K. Compactness and continuity. Theorem 2. If f from x to y is continuous on x, then f of k is compact in y for any compact subset k of x. Recall that f of k is equal to set of all f of x such that x belongs to the set k. Proof. Take any infinite sequence, set f of xn in f of k, then there is a subsequence xnj converging to x belongs to k. This implies f of xnj converges to f of x in f of k. Now we turn to see the generalized extreme value theorem. Theorem 3. Suppose f from x to y is continuous on k compact in x and y belongs to the set y, then there exists x belongs to k such that dy f of x comma y greater than or equal to dy f of z comma y for all z belongs to k. Proof. First we show that there exists m such that dy of f of z comma y less than or equal to m for all z belongs to k. Otherwise, for each positive integer n, we have zn in k, so that dy of f of zn comma y greater than or equal to n. Since k is compact, the sequence zn has a subsequence converging to z. Then by the continuity of f, dy of f of z comma y greater than n for all n, a contradiction. Next we prove the existence of x. As dy of f of z comma y is bounded on k, supremum of dy of f of z comma y is equal to m where z belongs to k is a real number. By supremum property, there exists xn such that dy of f of xn comma y converging to m. The sequence xn has a subsequence converging to x, and by the continuity of f of x equal to m. Remark. Actually, we do not need to assume x to be a metric space in theorem 3. We can proceed the proof by only considering open sets in x. The extreme value theorem we learned in lower classes is just the special case of this theorem. When we take x equal to y is equal to r, the real set, k to be a closed and bounded interval, d to be the usual metric and y equal to 0. Before we end this session, let us go a little bit deeper to the concept of uniform continuity. Some of the beginning analysis course includes this concept and some does not. Anyway, let us see the definition first. Definition 5. A function f from x to y is said to be uniformly continuous on a set S if for every epsilon greater than 0 there exists delta greater than 0 such that dy of f of x1 comma f of x2 less than epsilon whenever d of x1 comma x2 less than delta for x1 and x2 in S. Obviously, uniformly continuous are continuous. In general, continuity does not imply uniform continuity. However, in some conditions, the weaker one implies the stronger. Theorem 4. If f from x to y is continuous on a compact k, then f is uniform continuous on k. Proof. Suppose it is not the case, then there exists epsilon greater than 0 such that for each n we can pick an and bn in k, where dx of an comma bn less than 1 by n, but dy of f of an comma f of bn greater than or equal to epsilon. Now, the sequence an has a subsequence anj converges to a in k. Thus, bnj converges to a and f of bnj converges to f of a. To reach a contradiction, choose n so that j greater than n implies dy of f of anj comma f of a less than epsilon by 2. Then epsilon is less than or equal to dy of f of bnj comma f of anj less than dy of f of bnj comma f of a plus dy of f of a comma f of anj, which is less than dy of f of bnj comma f of a plus epsilon by 2 for all j greater than n. This shows dy of f of bnj comma f of a greater than epsilon by 2, which is wrong. Connectedness. Definition 6. A set A is disconnected when it can be divided into at least two disjoint non-empty subsets, say B and C, and each subsets can be covered exclusively by open sets, say U and V. That is, B is fully contained in U, comma, C intersection U equal to the null set. C is fully contained in U, comma, B intersection U is equal to the null set. Otherwise, the set A is called connected. Example: single points are always connected because they cannot be separated into two non-empty sets. Similarly, the empty set is connected. Any subset of the natural numbers is disconnected except the single points and the empty set. The set of rational numbers Q is disconnected. The connected subsets of R are precisely its intervals. Proof: let A be a connected subset of R. Let A comma B belongs to the set A and let A less than X less than B. Then if X does not belongs to A, it follows that open interval minus infinity comma X union open interval X comma infinity is a non-trivial partition of A, which is a contradiction for a connected set. Hence, X belongs to A, which means that A is an interval. For the converse, first consider an interval, closed interval AB. Suppose it should be connected. Then it can be split up into disjoint subsets B and C, each covered exclusively by U and V respectively. Suppose B belongs to the set B, which is fully contained in U, say. Consider the open set V intersection the closed interval AB, open in closed interval AB. Then this set is bounded above by B and is non-empty because it contains the non-empty set C. Hence, by the least upper bound property of the real numbers, V intersection the closed interval AB has a least upper bound alpha which is less than or equal to B. Now, alpha ought to belong to either U or V. If it belongs to U, then we should find an epsilon ball around it contained completely in U, but this would make alpha minus epsilon a smaller upper bound. If instead it belongs to V, then we can find an epsilon ball around it contained completely in V, but then there would be points of V larger than alpha. As both of these are contradictory, we conclude that the set closed interval AB is connected. Now consider any other interval. The intervals phi equal to open interval A comma A and the singleton set A equal to closed interval A comma A are always connected. So, suppose the interval contains at least 2 points and is disconnected. Then we can find 2 points contained in separating open sets A belongs to U and B belongs to V. But this means that the set closed interval AB is disconnected using the same open sets U and V, which is false. Hence, every interval is disconnected. Theorem 6. If f from x to y is continuous and A is subset of x is a connected set, then f of A is connected subset of y. Proof. Suppose f of A is disconnected into non-empty disjoint sets A and B covered exclusively by the open sets U and V. That is, f of A equal to B union C, which is fully contained in U union V, U intersection C equal to V intersection B equal to the null set. Then A equal to F inverse of B union F inverse of C, which is fully contained in F inverse of U union F inverse of V. F inverse of U intersection F inverse of C equal to F inverse of V intersection F inverse of B, which is equal to the null set. Moreover, F inverse B and F inverse C are disjoint and F inverse U and F inverse V are open sets. Hence, f of A disconnected implies A is connected. This means that the property of connectedness is preserved by continuous maps. In particular, a path which is a continuous function gamma from closed interval 0 on to x has a connected image. For example, straight line segments, circles and parabolas in R2 are connected. Corollary. Intermediate value theorem. If f from closed interval a b to R is continuous and f of a less than c less than f of b, then there exists an x such that a less than or equal to x less than or equal to b and f of x equal to c. Proof. We have proved that the closed interval a b is a connected set and hence f of closed interval a b is also a connected set in R. But connected subsets of R are just intervals. Now, f of a comma f of b belongs to f of closed interval a b, that is c is equal to f of x for some x belongs to the closed interval a b. Similarly, a continuous function f from closed interval 0 on square to R has the same property. If f of a less than c less than f of b, then there exists an x belongs to closed interval 0 1 square such that f of x is equal to c. By the above theorem, this remains true if we substitute closed interval 0 1 square by any connected subsets of R2. Let us summarize the major points discussed so far. A set is bounded when the distances between any two points in the set have an upper bound. The least such upper bound is called the diameter of the set. A set B is bounded when it can be covered by a ball. A set B is totally bounded when it can be covered by a finite number of epsilon balls, however small epsilon. A totally bounded set is bounded. The set S is compact if any infinite sequence in S has convergent subsequence in S. Let C be a collection of some open sets. If S is fully contained in union of U, where U belongs to C, then we say that C is an open cover of S. C is called a finite cover of S if C is an open cover of S with finitely many elements. D is called a subcover of S with respect to C if D is fully contained in C and S is fully contained in union of U, where U belongs to D. S is compact if and only if every open cover of S has a finite subcover. Any closed subset S of a compact set K is compact. Any intersection including uncountable of compact sets is compact. Finite union of compact sets is compact. If f from x to y is continuous on x, then f of k is compact in y for any compact subset k of x. Suppose f from x to y is continuous on k compact in x and x belongs to k, then there exists y in y such that dy of f of x comma y greater than or equal to dy of f of z comma y for all z belongs to k. A function f from x to y is said to be uniformly continuous on a set S if for every epsilon greater than 0 there exists delta greater than 0 such that dy of f of x1 comma f of x2 less than epsilon whenever dx of x1 comma x2 less than delta for x1 and x2 in S. If f from x to y is continuous on a compact K, then f is uniform continuous on K. A set A is disconnected when it can be divided into at least two disjoint non-empty subsets, say B and C, and each subsets can be covered exclusively by open sets, say U and V. Otherwise, the set is called connected. The connected subsets of R are precisely its intervals. If f from x to y is continuous and A is subset of x is a connected set, then f of A is connected subset of y. Intermediate value theorem. If f from closed interval a b to R is continuous and f of A less than c less than f of b, then there exists an x such that A less than or equal to x less than or equal to b and f of x is equal to c. Now, you may try to attempt the questions given here. First one, show that any subset of a bounded set is bounded. The union of two or finite number of bounded sets is bounded. Repeat the exercise with totally bounded sets. Second one, show that in R, a bounded set is totally bounded. Third one, show that compact sets are closed and bounded. What about the converse? Fourth one, show that the closed interval 0, 1 is not compact in Q by finding an infinite open cover that does not have a finite subcover. Fifth one, show that any intersection and any finite union of compact sets are compact. Sixth one, show that the only connected subsets of Q are the single points or the empty set. And the last one, let y be a positive real number. Use the intermediate value theorem to show that nth root of y exists. I suggest the following books for your further reference. First one, Principles of Mathematical Analysis by Walter Rudin, McGraw-Hill Book Company, Auckland, 1985. Matrix Spaces by P.K. Jain and K. Ahmed, Narosa Publishers, New Delhi, 1993. Third one, Topology by J.R. Mungers, Prentice Hall of India, 1991. Fourth one, Introduction to Topology and Modern Analysis by G.F. Simmons, McGraw-Hill, 1963. And the fifth one, Matrix Spaces by B.K. Tyagi, Cambridge University Press, New Delhi, 2010. Hope that you have enjoyed with this session. We will meet again with another topic. Thank you.